So we talked about numerical analysis and how important it is to investigate errors. But the natural first question is, what is an error? So here is the situation. We have some quantity, let's call it x, that we want to know. But for some reason, instead of x, we actually arrive at some approximation. Let's call it x hat. Now, error, intuitively, would be somehow related to the difference between these two numbers, or in other words, the distance between these two numbers. So for instance, this could be a reasonable notion of error. I would take the precise value and subtract the approximate value, the one that I actually have on hand. But of course, somebody may say, why not the other way around? And that's a good idea as well. So this could also be error. And perhaps somebody says, wait a second, we are talking about distance here. And distance, that's an absolute value of the difference. So that's another good candidate for the error. And if you go through various books on numerical analysis, you will find that authors actually pick out of these three. Of course, you pick one and then you stay with it because you want to be consistent. But you will encounter throughout the books all three possible versions of the definition of so-called absolute error. Now, intuitively, I am a little bit partial to the last one because it provides me with the information that I want. How far is my guess from the actual value? Well, absolute value is actually not really, let's say, convenient in calculations. So I think that most authors, including me, chicken out and do not use this one. Instead, we use the version without absolute value, and there it's more or less a toss of a coin. There is not really much difference between these two approaches, but of course you have to settle on one. And I decided to settle on the first one. So for me, and in this course, and therefore also for you, this first expression will be the absolute error of some estimation. We have a quantity that we want to know, its estimation, and that's the absolute error. I'm not actually losing on information because when we will be investigating absolute error, I will be using this nice formula for calculations. But then after I find the answer, I just stick it in the absolute value and I get the information about the size of the error anyway. Okay, so this is like a compromise, the best of both worlds. Good calculations and I get the answer. Is this notion reasonable? The answer is actually yes, we do encounter it in many situations. Let me show you. Here is an example, which could be also seen as experiment. Okay, you have a stick and you want to know how long it is. So you get a ruler and you line up one end of the stick with 0 and you look at the other end of the stick. Here we go. This is a ruler in case you didn't recognize it. And let's say here is mark 13. Here is mark 14. I'm going by meters, but you can pick whatever unit you want. Now, in the middle somewhere here, there is a medium-sized bar, and then there should be 4 small ones. Let's see. I guess that could be about it. Yeah, that looks reasonably like a school ruler. And now, here at 0, I line up one end, and the other end comes, I don't know, here, for instance. So I look at it and I would say, okay, I think that my stick has length, I guess, 13.6 centimeters. Or if you want, L is 136 millimeters. Now, obviously, this is not the precise length of the stick. Perhaps I could also make a guess about another digit, but it would be a guess. But with this, I'm sort of reasonably content. It would be dangerous to venture any farther. And it's also equally obvious that I'm making an error. Now, what kind of error? That's a good question. And of course, if you don't know how to calculate something, you go to definition. So here's the definition. To find the error of my guess, I would have to take the actual length of the stick. Where do I get it? Now, this is a problem, fundamental problem. If you want to find the absolute error, you need to know the actual value, the precise value. And if you know the precise value, why would you guess another value which is not even precise? So this doesn't really make much practical sense. So instead, what we very often do, we try to find an upper estimate for the absolute error. And that's something where we have a good chance. Why? Well, let me see. How did I get my measurement? I looked at the end of the stick, and I went to the nearest tiny bar. Now, assuming that I'm not like totally clumsy and that I do it properly all the time, it seems that the largest error that I can make is exactly half the distance between the two neighboring bars. So the error is bounded by 0.5 millimeters. And this is typical in several meanings, actually. First of all, this is typical for applications. We get an upper bound for the absolute error, and many authors, but not all, use lowercase e for that estimate. So that's something which is very typical. Another typical thing is that you get this type of error when you are using measuring devices. Now, if you are measuring something which is continuous in nature, like weight, length, energy, things like that, temperature, then you have to use some measuring device which has granularity. It is never precise, not completely precise. So when you buy, let's say, a slightly more advanced measuring device, there should be a sticker which actually tells you what is the precision in terms of absolute error. So this absolute error, that's a very useful notion which appears pretty much every time you're asking how large is it, how, and so on. So this is natural. Now, what kind of information can I get out of this? Well, let's have a look at the formula here. When I rearrange it, I find that the actual precise value is the approximate value plus the error. As we talked about it, I unfortunately do not know the error. So this is not practical, but it will be helpful theoretically. We will see soon. Instead, what I have is this. I know that the error in absolute value is bounded by some estimate of my x, and the error is the absolute value of x minus x hat. And it's not really difficult to rearrange this into the following form. The precise value must be hidden between x hat plus the estimate ex and x hat minus the estimate ex. So we are getting a range for the precise value out of our measurement and the knowledge of the absolute error. And this actually is very popular, so there is a shortcut notation for it. X is x hat plus or minus ex. And that's a very popular engineering notation. For instance, in my case, I would say, okay, the length of the stick is 136.0 plus or minus 0.5 millimeters. Now, engineers, they have some rules of how to write this properly, and of course, one of the most obvious rules is that the unit here and the unit here, they have to agree so that these two numbers can be put together, okay? Also visually, you just look at it and you see what's the range, what's the uncertainty. That's a good word. There is actually a theory about it, but we will not go into it here. Okay, so it seems that absolute error is a very good thing to know, but the key question is, you do some measurement, you learn about your absolute error, and now you want to know whether your measurement is reliable or not. Is it good or is it worthless? So let's have a look at the situation. Imagine that you still have some measuring device which has absolute error at most 0.5 millimeters. And now let's say that we measure something. Let's say something practical. Let's say the distance between my bed and the bus stop. Okay, that's a very important piece of data when I'm optimizing my early morning routine. So I look at it and I don't know, 423 meters. Now, following the advice that we obtain over here or over here, I could write my findings as follows. X is equal to, now I'm careful, I need it in millimeters. So it will be 423,000 plus or minus 0.5 millimeters. That would be the conclusion. And I look at it and I would say, this is really precise. Yes, In fact, I would say this is really suspiciously precise, because when I see those 3 zeros here, this is very unlikely. When I see a result like this, I would rather guess that the precision was something like a meter, or let's say half a meter, or something like that. Obviously, somebody was just estimating. Well, I was just guessing, so I was suspicious rightly. But if this really were a precision of my measurement, that this is even needlessly precise, because precision costs money. The more precision you need, the more expensive measuring device you have to buy. So I would say that here I was actually wasting my money if I really measured the distance between my bed and the bus stop with precision 0.5 millimeters. I strongly suspect there is some mix-up in the data. On the other hand, imagine that I'm measuring the thickness of my hair. Now, I actually haven't done it, but I looked it up on the internet, and it seems that if I obtained 0.08 millimeters, then this is not really off the mark. Could be something like that. Now, again, let's write it. X is 0.08 plus or minus 0.5 millimeters. Now, does it look like a good measurement? Definitely not, because the error, the width of the range for my value, is much larger than the actual value itself, the one which I calculated or measured. So the error actually overwhelms totally the data which I obtained from my measurement. I mean, if you subtract, it would even seem that the hair could have a negative thickness. Well, that could explain a lot, but still, I really find it highly suspicious. And in fact, such a measurement would be considered highly unreliable and not usable at all in applications. You definitely do not want the error larger than what you measure. So the conclusion is that if you want to judge the quality of your measurement, you shouldn't be looking just at the absolute error, but compare the absolute error with the number that you obtained from your measurement. That is the right measure of reliability of the result. And I think that we are ripe for some slide. Here we go. I can see the definition of the absolute error, and I hope it's the same. Yeah, it's the one that I picked here. And then I can also see the definition of a relative error, which is exactly what we talked about here, comparison. In mathematics, comparison is done usually by division. So we ask how large the absolute error is, that's the absolute value, I've been talking about it, and divide it by the magnitude of the precise answer. And there you can see the problem again. Typically, it's impossible to find the relative error, but very often we have good information about the upper bound of the relative error. Down here, we can also see a note about the upper estimate for the absolute error, which is commonly denoted lowercase ex. But not universally. And what we really want is the upper estimate. This is common sense, because we want to keep the error down. And you keep things down by having good upper estimate. It would be also nice to have a notation for some estimate of the relative error, but I'm not aware of any notation which would be, let's say, widely accepted. So I didn't put there anything. We will just say upper estimate, things like that. Okay, now let's have a look at the situation. We will soon see that there are many settings where we actually have information about the relative error. We have upper bound for it. So can I get some information from knowing the relative error? And when I look at a formula, I can see right away that the absolute error is the relative error times the precise value, which is not exactly convenient, as we already saw about twice. So what can I do if I actually do some practical application, some practical calculation, and I want to get some information, but I don't know the precise value x? Well, there are two approaches. The first one is very useful, but one has to be very careful. It's an engineering approach. An engineer would say, okay, I want to know the absolute error. Now what happens if I replace the precise value with my approximate value? Do I make an error? The answer is yes, but small, if I'm lucky. Okay? Sometimes, perhaps, I have information that my error is small, which, after all, I can see from the relative error. The relative error should definitely be a small number, unless I did something really bad. Okay? And if the relative error is a large number, then I can throw it out anyway. So I can expect relative error to be tiny, and therefore these two numbers should be close, hopefully. Now, as you can see, this is dangerous, but it's also very practical. So it has to be done, let's say, with experience and with knowledge of what can go wrong. Of course, for a mathematician, this is not exactly okay. So let's have a look at how a mathematician would handle it. So let's put it aside. As a mathematician, I want precise calculations, and I want to pass from x to x hat. That's my motivation. So I would say, okay, is there any connection between x and x hat? And the answer is yes. I've got this formula. The precise answer is the approximate answer plus the error. And now I will apply the triangle inequality to this part, and I will get that the absolute error in absolute value is epsilon x, and now the triangle inequality forces me to put inequality here, and I get x hat plus ex in absolute value, each of them separately. I had to put the bracket here because the relative error multiplies the whole group. I have to make sure that it still multiplies the whole group. Now I multiply out, and I move the absolute error to the left. Little trick. What do I get? I'm moving it to the left. I'll try multiply it out. And on the right, there will be epsilon x times x hat. And finally, I factor out the absolute error. And I divide by whatever is left. I'll try factor out. So I get epsilon x over, I pull it up, I guess 1 minus epsilon x, x hat. Is this valid? The answer is, well, not in general, because I've been dividing by this number, and I need this number to be positive so that I can keep the inequality. Is it reasonable to assume that this is positive? The answer is yes, because if the epsilon x, that's a relative error, is 1 or even more, then it means that my estimate x hat is worthless and I don't want to work with it anyway. So if this x hat estimate is any good, then definitely relative error should be close to 0, and therefore this number is positive. So under this assumption, this calculation was correct. This is mathematical formula which is reliable. We just proved that it's true. Let's compare it with the engineering formula. They are remarkably similar, and if my measurement is really good, then the relative error is almost 0, and this denominator is almost 1. We can ignore it, and we get the engineering formula. Okay? So that's a nice relationship between precise mathematics and engineering point of view, which is not precise, but it sends the right message. And it's important to understand things. If you are using numerical analysis in applications, you should understand what it says. Okay? So it's useful to also have this kind of information. Now, we just saw that there is a relationship between the absolute error and the relative error, because once we have the absolute error, some bound for it, either the precise one or the engineering ones, we can start talking about intervals of reliability, things like that. So let's ask crucial question. Let's say that I learned that epsilon x is a specific number, a certain number. What does it tell me about my measurement? That's a very good question. And as I say, we now prefer to see intuitive information. So let's skip precise mathematics for a while, and let's have a look at an example. Imagine that I measured something, and the answer which I obtained was, let's say, 2, 3, 4, 5, 6, 7, 8, 9. Let's make it nice. Okay. And then, from some source, I learn that the relative error is, okay, I should write bounded, but let me write equality for simplicity, 1 over 100. Which is, by the way, 10 to negative 2, which we, of course, know, but I think it's useful to see both informations in the picture. So, what does it tell me about the precise value that I was after? What is the range for it? Well, let's have a look at it. This is my measurement. 2, 3, 4, 5, 6, 7. I should have taken a shorter number. Okay, what is the absolute error? Because we need the absolute error to see the range, over here or over here. So, the absolute error is bounded by a number which I obtain by taking the relative error and multiplying the estimate with it, the approximation. So I take this approximation and I multiply it by the relative error. What does it do to it? Well, it will shift the decimal place by 2 places to the left. So the decimal dot goes 2 places to the left, which means the number as such shifts by 2 to the right. And it will be 2, 3, 4, 5, 6, 7.89. Okay, so that's the error. So what is the range for the actual value, for the precise value x? Well, I look at this error and I add it or subtract it from this number. And when I add it and subtract it, it will change the digits here. So these digits, they can change. I don't know anything about them. But these two will not change definitely. So these 2 digits are there, and there are some other digits. And this is something that I know for sure. So my conclusion is that if I have some measurement, and I learn that the error is 1 over 100 or 10 to negative 2, then it seems that I can trust 2 digits of this answer, the first 2 digits. Interesting. What happens if I learn that the error, relative error, is 1 over 1000? Well, it seems that I can repeat the same trick and I find that the error, the absolute error, will change it by, okay, let me shift it by 3. And some things are happening here, I don't care. And when I again repeat the same trick, repeat the same reasoning, I will find that the precise answer for sure starts with 2, 3, 4, and then there will be some digits. So it seems that here I can trust 3 digits. Now, can you see the pattern? 10 to negative 2, 2 digits. 10 to negative 3, 3 digits. Or 2 zeros, 3 zeros. 2 digits, 3 digits. This is very nice. This is the intuitive meaning of relative error, if it is in this form. But since we are looking for upper estimate usually, we can always perhaps add a little bit more so that the estimate for relative error has this nice shape. Another important thing is that if you can decrease relative error 10 times, you will add another reliable digit to your result. Or vice versa, if due some, let's say, accident, your relative error is multiplied by 10, then your result actually loses 1 digit of reliability. Okay? Now, I would like to write it as a theorem because it's important, but I cannot write it as a theorem because we don't have a reliable digit as a mathematical notion. And it is possible to define it mathematically, but when you try it, you will find that it's actually very difficult. I don't want to open this question even. It's a can of worms. I don't want to go into it. So let's stay on the, let's say, intuitive level. Okay, here we go. If the relative error is bounded by number 1 over 10 to p, which is 10 to negative p, then my estimate x hat has p reliable digits. And this is really informal statement, not a mathematical statement, so I will just erase it quickly so that nobody can see it, but let's appreciate it. But before we appreciate it, notice this big gap here. This is not the usual space between words. I will have to do something there. Let's have a look at the situation where the relative error is 1 over, and now I put 4 zeros. When I put 4 zeros, the situation goes like that. 2, 3, 4, 5, 6, 7, 8, 9. I shifted by 4. 1, 2, 3, 4. 2, 3, 4, 5. And now, imagine what happens if you add. If you add these two numbers, then you will get something more than 10. You carry 1. It comes here. Things start getting really difficult. And if you are unlucky, well, perhaps I will add another 0 so that we can see it better. Yeah, it will be better. So this will be 2, 3, 4. When you get unlucky, notice that I have 1, 2, 3, 4, 5 zeros. So perhaps I could trust 5 digits. But it's not true, because there is this carry over 1, which comes here, creates 10, carries over, and suddenly I get 7 here as a possibility. So I can no longer trust 5 digits, but only 4. But perhaps you can easily imagine if these were 9s, then this carry over 1 would make a domino effect and change all of them. So that's another reason why I cannot make this into a mathematical statement, because it's not true actually. So just to be on the safe side, I will put p minus 1 digits here. So when you have relative error 10 to negative p, you have p minus 1, to be on the safe side, reliable digits. This is still not true, but it's almost true. In most cases, this will work for you. So this is the intuitive meaning of a relative error. It actually goes both ways. And to see that, we will need a lot of room. So we talked about absolute errors being related to measurements. Now, relative errors, they are closely related to the way numbers are stored in computers and calculators. Now, you probably think that there is little problem in storing information in the form of integers and perhaps fractions, and that's essentially true. Unfortunately, for engineering calculations, we have to go beyond rational numbers, fractions, things like that. We also need some irrational numbers, and for calculations to work well, we need them stored in a decimal form. Now, when you take an irrational number and write it as a decimal number, it has infinite expansion. So how do you store it in a computer? That's a problem. There is a trick for it, of course. Let's have a look at it. So I have a number, let's say 13.2567. And I want to store it in a computer. So typically, computer would first fix the position of the decimal point. And there are actually 2 ways or 2 widespread possible positions for the decimal point. And for this course, I chose the one which is behind the first significant digit. So I would write it as 1.32567. And now I have to add times 10 to 1. The competitive school of thought thinks that the best position is in front of the first decimal digit, the first significant digit. And also you can develop the theory in a similar way. I think that this one is slightly more convenient and also slightly more widespread. So I'm sticking with this one, okay? So we have a digit, non-zero digit, that's important, decimal point and some digits, and the exponent, which is shifting, which is positioning the decimal point to the right place. And now, here comes the trick. We need to store only a specific part of this decimal expansion because it could be potentially infinite, and perhaps even this one is too long. It depends on the memory that we have. If you have a very, very tiny computer, then it can perhaps store only 4 digits. So if the computer can only store 4 digits, it would go, well, that's a good question. Actually, again, there are 2 possible approaches. In some systems, they use so-called truncation. And truncation works easily. You just ignore whatever you don't want. So I want 4 digits. Let me put it here. P is equal to 4. I want 4 digits. So it's 1.325, and I just ignore the rest. Times 10 to 1. The other possible way is rounding. And I would say that this number is 1.32, and here I am going to round up to 6 times 10 to 1. Now, in some systems, you can really find this truncation, and the advantage is that it's quick, simple, no problem there. Disadvantage is that it's slightly less precise. So for engineering calculations, especially if they are important, and they are all important, of course, you would prefer rounding. Now, before we get into the format and so on, let's address one interesting question. What if I asked for this number to be stored on an even tinier computer with a really tiny memory, okay, which remembers just 3 digits? Perhaps I will start with a slightly modified example. Let's say that I started with 1.325. What do I store when it comes to 3 digits? Well, when I was at elementary school, they told me that 5, which comes after the last storable digit, should be rounded up all the time. So at elementary school, I would say 1.33, and the teacher would say, okay, that's nice, and check the answer, and I would get points or whatever. However, this is dangerous. Why? Rounding works like that. You have two digits or two numbers that you can remember. I can remember 1.32 and I can remember 1.33. And that's all I can remember. Now, if I get a number which is somewhere in between, then if it's closer to 1.32, I will round it down. If it's closer to 1.33, I will round it up. So that's quite obvious. However, 1.325 is exactly in the middle. So it has exactly the same distance from these two numbers. Now, if I keep rounding these numbers all to the top, then I'm actually introducing a bias into my calculations, because this is unfair. These numbers are exactly in the middle, and I'm pushing all of them up. And this can be also dangerous, because if you have a bias in your calculations, it could actually shift the result in the wrong way. This can be a serious problem. So in engineering, what they need is to round such numbers sometimes up and sometimes down. Ideally, half the time up, half the time down. But this cannot be achieved in such a way because you would have to keep track of your roundings. You would have to store somewhere in the memory information how many times you rounded up, how many times you rounded down. This is impractical. So instead, engineers came up with an interesting idea. They said, okay, you round in such a way that the resulting number has an even digit at the end, which is convenient. You can divide by 2. It's very nice. So actually, this is not proper engineering rounding. We should be rounding it to 1.32 by the engineering standard. Now, quite frankly, this is totally off the topic of this course. We don't have to worry about it. But I think it's curious that people in applications, people who work with real-life calculations, they actually see things differently compared to what I learned as a student. So, yeah, this is just an interesting side note. Let's not worry about it. Let's worry about this. Okay? We have a number, and we change it into a number which has a specific form, and we keep just a part of it. This is called floating point representation, and if I remember correctly what I was typing, we should be seeing it right here, and we do. So, when you have a number x, in computer it is replaced with a different number, which is called FLX very often in books, and it has a specific form. You specify at the start how many digits you want to store. Now, these digits then can be anything between 0 and 9, but the first digit cannot be 0, obviously. There is one exception, of course. If you want to store 0, you simply store 0, no problem there. But for the other positive numbers, this format is quite clear. Key question. Instead of this number, I'm storing this number, or this number perhaps. I'm making an error, definitely. You can see it here. How large is the error? Let's have a look at the situation closer. I have my number, and let's say that I already shifted the decimal dot. So it's in the following form. There is the first digit, dot, the second digit, the third digit, and so on. Then there is the p minus first digit, and I still remember this one, pth digit, and p plus first digit, and so on. Many, many digits, and then there is the shift by some exponent. In my computer, this gets stored, or in my calculator, as a floating point number, which starts in the same way. Now, actually, that need not be true, because if we are using rounding, then there could be this carry over 1 traveling, and domino effect changes even this one. So I'm going to simplify my life now. I'm going to ignore the situations with carry over 1s. So let's be optimistic. I stored these p minus 1 digits, which is what I did over here. I stored the first 3 digits easily. But the fourth digit, there I have to worry about rounding up or down. So there will be some digit, let me call it capital DP, and it could be either little dp or dp plus 1. Okay, it depends on the tail here. Now, what is the absolute error? And there is, of course, this shift. The absolute error of this number I obtain by taking the precise value and subtracting the approximate value. So I'm subtracting, and of course I can see that all these places, they cancel, these digits. So O, 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 O. How many O's? The answer is p minus 1, because I can see this is the first one, second one, third one, and so on. At the end, of course, there is this, 10 to e. Now the question is, what should I put here? That's a very good question. And to simplify my life, I will ignore this decimal part here. Let's imagine that the decimal dot is somewhere here. So I'm just comparing two numbers. And I want to know the difference. Now, there are two cases. One of them is when I'm rounding down, so capital DP is the same as little dp. And then when I'm subtracting, then this tail actually tells me the error of this approximation. Now, what can I say about this error? Well, remember, we are talking about the case when I'm rounding down. If I'm rounding down, then this digit can be 1 or 0, 0, 1, 2, 3, 4, and even 5, if there are all zeros afterwards, but not more. So this digit cannot be more than 5, and therefore the error cannot be more than 0.5. And now I shift the decimal dot back. I don't have to look at it intuitively anymore. Okay? Or the error could be less. So let me put it this way. That's the case when we are rounding down. What is the error when we are rounding up? In that case, I'm increasing this digit by 1, but in order to do that, this digit should be 5 and something behind, or 6, or 7, or 8, or 9. So it's actually really close to this new digit as a number. Okay, if you imagine there is this number dp, there is this number dp. Let's ignore whatever comes in front of these two guys, okay? Because it's the same, so we can ignore it. Just let's focus on this. If I look at this tail, in order to do the rounding up, I have to be in this range. So the error which I make by rounding up cannot be more than half the distance between these two guys, and half the distance between these two guys is 0.5. Okay? This fits. If you do not see it, try it with some numbers, with some particular numbers, concrete numbers, and you will see how it works. Okay? Anyway, this is the absolute error. What is the relative error? Well, by definition, this should be the absolute error divided by the relative error. By the actual value, the precise value. Let's estimate. In the numerator, I have an upper estimate for the absolute error. 0.0 O's. How many O's? The answer is P of them. First, second, third, pth. So there is P, zeros, and 5, like that, times 10 to e. Divided by, and I don't want to put x there because it would be in the answer, and I don't want it there. I just want one nice real number, preferably. So what I'm going to do, I will replace this x with a lower estimate. Okay? I want to increase the fraction, and we increase the fraction by making the denominator smaller. So what is the natural lower bound for this number? I will just take all these digits, and I push them down as low as they go. So these digits can be pushed down to 0, but this digit can be only pushed down to 1. So the natural lower estimate is 1 point and some zeros perhaps, times 10 to e. Now let's see. 10 to e cancels. Here I'm dividing by 1, so I'm essentially not dividing. And here is 5 times. And how many times do I have to shift the decimal dot so that it appears here behind 5? And the answer is p. I said it. I've been thinking about it already. So it should be like that. And again, if you don't see it right away, try it with some concrete numbers, 0.0005. And you try to shift the decimal dot. You try it a few times, you will see that it works. Okay, so what we have here is an upper bound for the relative error when the numbers are stored with p-digit precision. And that's exactly the relationship I've been talking about. Every time you enter some number in a computer or calculator, this computer or calculator has some p-digits. This is a fixed parameter of the system that it remembers. And therefore, you can count on making an error, relative error of this size. Now, let's revisit this. Intuitively, it seemed that if the relative error is of the form 10 to negative p, then I can trust p digits. Okay, p minus 1, but let's be generous now. I can trust p digits. Here we found that if we can store p digits, and when I'm storing them, I'm trusting them, of course. So if I can store or trust p digits, then the relative error is 10 to negative p. Again, I'm losing actually 1 power here. This is less than or equal, and if I put 10 instead of 5 to increase it, it cancels here, and I get this. So again, there is a shift by 1. Okay, so it doesn't work precisely both ways, but each way I'm essentially losing 1 digit or one power of 10. So this confirms that there's a really close, both-sided relationship between how far I can trust a specific number and the relative error. So that's a very important confirmation of our intuitive feeling, but it's also a very important information. When you store a number with a computer, there is a certain precision, and you cannot really hope that you will get anything better. This is the baseline precision, relative error precision, for numbers that you store in your computer. Of course, if you are storing integers, that's another story, but once you store decimal numbers, you are in trouble. When I was young and naive, I thought that perhaps if I store 1.8, then actually I'm not making any mistake. Well, actually, my calculator, when it sees number 1.8, it changes it into a binary code. And when it changes it into a binary code, 1.8 happens to have infinite expansion. So there will be infinitely many zeros and ones, and the computer or calculator stores just a few of them, and here is the error which I'm making. So even if I put a really cute number into my calculator, I'm still making an error immediately with this relative error as an upper bound, unfortunately. Of course, if I chose a different number which is cute, perhaps it would be cute also after transforming into binary code, but I'm not good enough to do the calculations in my head immediately. So essentially, the bottom line is when you are putting numbers into a computer, this epsilon, that's something that you have to count on. This should be appearing immediately, most likely, in your calculations, this error. Okay, which brings me to the last topic of this error chapter, or the error topic. We put some numbers into our calculators or into computers, and those numbers get distorted by some relative error that you have under control, fortunately, but then you start calculating with them. How do these errors on the input influence the outcomes of your calculations? That's a very good question and a very important question. So that's our next topic. Let's make some room. Imagine that you need to add 4/9 and 4/9. Now, if you do this calculation with a pen and a pencil, you will get 8/9. And that's a precise answer. If for some reason you need to do this calculation in our calculator, and let's say that it's a very tiny calculator with a tiny memory, just 2 digits, 4/9 would transform into 0.44. And that's it. Now we know that the actual value is 0.444444 and so on. It's a periodic number. But the computer doesn't know it, or calculator. It's just 0.44. And another 0.44, and when this is added, you will get 0.88. However, the precise answer should be 0.89. So you can see that the answer is not precise, and one of the things where things got wrong was already here on the input. When you entered number 4/9 into the calculator or a computer, there was a tiny mistake, and these two mistakes, they sort of added up and created this mistake. So that's the key question for this moment. What happens to errors on the input when we are applying algebraic operations to these numbers on the input? Let's have a look at a slide. Here we can see that we have two numbers, x and y, and let's assume that they are positive. This will make our life easier a little bit. And on the left, we can see what happens when we try to add them, subtract, multiply, divide, and then there is a special operation. And we can see the absolute errors of the outputs. So let me focus on the first formula to appreciate the meaning of that formula. I have two numbers, and I want to add them. So this is the ideal outcome. But unfortunately, due to working in a computer, I'm instead adding some approximations. And when I add them, I get approximation of the sum. And I would like to compare these two outcomes. So what is the absolute error of this outcome? It's the absolute error of number x plus y. And now when you are reading definitions, it's good not to worry too much about individual letters, but rather think of notions. So what is the absolute error? What does the definition say? It says you take the precise value and you subtract the approximate value. So the precise value is x plus y, and the approximate value is x hat plus y hat. That's what we calculated instead of what we should have done. Okay, you could take this and claim that it's the answer. Yeah, that's a formula, it's a mathematical formula, so what else would you want? Actually, our main motivation is to somehow find the error of the outcome as it depends on the error on the input. So I would like to rearrange it in such a way that I can see the absolute error of x and absolute error of y. That's my main motivation. Here it's actually quite simple, because I can just reorganize, open this bracket, and I get x minus x hat plus y minus y hat. And I can introduce new brackets, and I look at it and I say, oh, wait a second. This is obviously error of x plus error of y. That was easy. Now, let me put it here. That's a nice mathematical formula which takes the error on the input and shows me the error on the output. This error can be positive, negative, so they may cancel. It may happen if you get lucky that the outcome is actually more reliable than the input, but you cannot count on it. In numerical analysis, we should be pessimists and make sure that the pessimistic case is still good enough. That's the idea. So let's be pessimists. The largest possible error that we can make when adding two numbers like that is bounded by, and now again, triangle inequality, our friend in need, it's ex plus ey. Here we go. And that's the formula that we can see in the left column on the top. Then we can see formula for subtraction, and the proof is actually the same, more or less. It's just a minor modification. The third formula for multiplication looks less easy, less nice, and it actually is not nice at all because the x and y numbers are appearing in the answer. Here this is beautiful because we just look at the information about the errors on the input, combine them, and get the information about error on the output. But there, x and y interfere, but we cannot do better. Let me show you the proof. So, we are interested in the error of the number x times y, which is the actual precise value minus what we calculated in our calculator instead. Now you can see the difference between the two, because here I could just rearrange and I got exactly these subtractions that I wanted to see. But here there is no way to somehow factor out y, for instance, to get x minus x hat. So if I want to get something, let's say, reasonably nice, I would have to do some trick. Here is a favorite mathematical trick. I would really love to see x minus x hat. If I want to see x minus x hat, I need to get rid of y, most likely by factoring out. So why don't I put minus x hat times y? Now I can factor out y, and I get exactly what I want. Unfortunately, there is equality here, which prevents me from just putting some extra term. In order to fix it, I also have to cancel it immediately. And now it's not there at all, and I can keep going with the above formula. So in fact, these two terms in the middle, they are not there at all. I have a right to put equality, but they're also there. Now, I factor out y from the first one, and I get x minus x hat times y. And now, this is where things get tricky. This part I did because I wanted it. But here I didn't have a choice. I had to add the same expression as is here, and there is no guarantee that this other part will work out nicely. So we have to keep our fingers crossed. Let's see. I can factor out x hat, and I get y minus y hat. Wow, we got lucky. So this is error of x times y plus x hat times the error of y. And now if we apply the absolute value, here we use triangle inequality and then distribute the absolute value inside the products, we should get exactly that formula. Is that it? Yep. There are two versions actually. One of them has hat with x and the other one has hat with y. It depends whether you put a hat here or here. It can come in two positions and both of them eventually work out more or less the same, okay? So that's the multiplication trick. Division is slightly more devious, but it's more or less the same story. The fifth formula is like a bonus. It's a special version of division where the numerator is actually known precisely. The number 1, it's perfect, it's integer, so there is no source of error with this number 1, just in the denominator. Okay, so this was just an aside. Let's focus on the addition. Because absolute error is useful, we couldn't do without knowing it, but for interpretation we want to know relative error. So let's have a look at the first line on the right, relative error. Okay, relative error of x plus y, by definition, is the absolute value of error, the absolute error of x plus y, divided by the actual value, x plus y. Okay, now let's see. For the numerator, we have a nice upper estimate. And for the denominator, we do not have anything yet, unfortunately. Okay, well, again, I could keep this as the answer, but I would love to see relative error of x and relative error of y somewhere in the mix here. So I have to introduce it there. Well, the first obvious step is to break it into two fractions. So we are getting ex over x plus y plus ey over x plus y, everything in absolute value. Now, here comes a dirty trick. I will break this fraction into two, which are multiplied. And of course, I want to keep things the same, so I put ex here and x plus y here. And I will do the same thing with the other fraction. So far, I didn't really change anything. This is just a different way of writing. I imagine that there is one here, one here, one here, one here. It's the same. But now here comes the trick. For some reason, I decide to put x here, and also here then. And then they cancel, and I'm still keeping the same equality here running. Here, for some reason, I put y in absolute value. And now I look at it and I say, oh, wait a second. This is the relative error of x. Wow, aren't we lucky? I talked about an assumption that x and y are positive, and this I will use here to get rid of absolute values. I prefer to have it like x over x plus y, and the relative error of x plus y over x plus y times the relative error of y. Here we go. Is it nice? Not yet, because I can see x and y in the answer. I really like those epsilons here, but not this part. I would like to factor out epsilon, but they need not be the same. However, another trick. I'm happy with an upper estimate, so I can replace these two relative errors with the larger of them, which will make things larger. So, what will appear there? Well, instead of epsilon x, I will put larger of epsilon x and epsilon y. So if epsilon x is larger, it will be here and it's the same. And if epsilon y is larger, it will replace this guy. And the inequality works. And I will do the same, exactly the same, with the other relative error. I replace it with the maximum. Now, this maximum is just one number, just one symbol, just one object. I can factor it out. Maximum epsilon x, epsilon y. And when I factor it out, there will be x over x plus y over x plus y. And this adds up to 1 and disappears. And that's the happy end. That's what we can see on the right. Okay. The other 5 formulas can be done using similar tricks. So there is really nothing more to talk about when it comes to this theorem and its proof. So from the mathematical point of view, we have it licked. Let's talk about the interpretation. And for that, we will pass to engineering approach. We will sort of like, let's say, close one eye so that we can see it a little bit fuzzy and say, oh, it's about like this. You can see that the mathematical precision forced us to do some complicated stuff on the right. When you look at the second last, the last row, you can see something with 1 over 1 minus epsilon x. We saw this before. This is exactly the result of trying to make engineering, let's say, guesses precise, passing from relative error to absolute error and vice versa, things like that. If epsilon x is really, really tiny, then it can be ignored in those ratios, and those formulas become much more pleasant, much more readable. So let's put another fact here, which is an engineering fact. This is not really a truly mathematical fact, although, okay, it pretends to be so, but okay, I'm making it clear that it's not. So imagine that you have some general rounding error, epsilon, or the upper bound for it. Epsilon is the upper bound for rounding error. Like we talked about it. Computers, calculators, they have this rounding error based on the precision, number of digits that they remember. And it's common. And now you have two numbers, and you decide to add them, multiply them, and so on, and you want to know how reliable the outcome is. Now remember, relative error tells you about the number of digits that you can trust, roughly. The first formula. It says that when you add two numbers, then the relative error cannot grow, which we also see here. The relative error of the summation cannot be larger than the relative error on the input. And there is also multiplication by a, and this a is an integer. It's a number which does not have an error coming with it. So this is very nice. Let's go down. Let's make a chart. Theory. Addition. Addition is okay. We love it. Division and multiplication. You can see that they behave in the same way. When you divide two numbers or multiply two numbers, then the relative error doubles, which is not too bad. Multiplication, division, okay. But let's ask this question. What happens if there are 4 multiplications in your calculation? Each multiplication increases the relative error by 2. With 4 multiplications, you are getting the original relative error multiplied by 2, by 2, by 2, by 2, which is 16 times epsilon. And 10 times epsilon means that you lost 1 digit of precision. In fact, for every 3 1/3 of multiplications or divisions, you can potentially lose 1 digit of precision. And then you have to start worrying. So when you have many multiplications, many divisions, you should be careful about keeping precision of your calculations reasonably good. So I have to put here, it's okay when there is just few of them. And for the last, I left the second operation, which is subtraction. This one is exceptional. You can see that there is x and y appearing in the result, which is something that we do not want to see, but there is no way to avoid it. It must be there, unfortunately. And let's see what the coefficient is. Now, here the coefficient was 2 for multiplication and division, and we already observed that it could complicate things. There, the number x plus y over x minus y could be as large as you want if x and y are close. So the relative error could blow up totally if you're subtracting two numbers that are very similar. And that's a frowny here when close. I mean the numbers. I don't have too much room. Let me give you a common sense explanation why subtraction of similar numbers is a big problem. Let's say that you have a number and you can trust 4 digits. Why not? A, B, C, D, these are the digits that you trust. Then there is E, F, G, H, I, let's say. And you are subtracting another number where you can also trust 4 digits. And this number is very similar. And because it's very similar, then the first digits are the same, but the last 3 digits are different. And now you subtract them. And when you are subtracting, then these digits, which are the same, they cancel each other out. And the result is actually determined by this part of the numbers. And that's exactly the part that you do not trust at all, which is influenced by the error that you have here. So you can see really, without any knowledge of theory, that when you are subtracting similar numbers, you shouldn't really trust the result much, unless you have it under control. This is very difficult and very dangerous. So when you look at this, let's say, intuitive version or engineering version of the theorem, or we look at this chart, this is what we call propagation of error in operations. You start with some errors on the input, and you're asking, what happens to them? How do they influence my result? And when it comes to addition, for instance, you can see that actually the answer is as reliable as the question, essentially. It may even get better if you get lucky and those errors cancel each other out, which is the case also for multiplication, division, subtraction. If you get lucky, it's okay, but there is no guarantee that you will get lucky unless you are really good. This is the theory, the propagation of error in calculations. By the way, you can also ask about propagation of errors when you substitute into exponential, into sine, into tangent, into logarithm, things like that. I made a little note about it in the lecture notes, so if you want, look it up. By the way, Taylor expansion is a very good tool there. We will talk about Taylor expansion here a lot. Very good tool in numerical analysis. Let's talk about practice. Addition. Addition was really good, theoretically. What happens when we try it in an actual computer? Actually, it turns out that there may be a problem. And the problem happens when those numbers are very different. And I should have some room here. Yeah, I remember it correctly. Let's say that you have 1300. And you want to add 13 on a computer. So the computer stores these two numbers. It stores 1.3 times 10 to 123, 10 cubed, plus 1.3 times 10 to 1. And it's a computer which stores only 2 digits. It's a very basic computer. So these numbers are stored properly. 2 digits here, 2 digits here. Now here comes the problem. If you want to add 2 numbers in a floating point form, you need to have the same exponential term here. You need to unify the exponents. And this is done by going to the larger. So you still keep 1.3 times 10 to 3. And here you want to see at the end 10 to 3. How do you get 10 to 3? By moving the decimal dot 2 places to the left. So what you should put here is 0.013, really. But the computer only remembers 2 digits, which is these 2 guys. So the computer puts 0.0 here and looks at it and says, okay, this is 1300. As you can see, there is an error here at the end. Very unpleasant, and this can get out of hand if you are doing a lot of calculations when you're adding a lot of really tiny numbers. This can be fatal. There is a real-world application where people who were programming the system overlooked this, let's say, this trouble, this potential trouble, and it actually had disastrous consequences. The system wasn't workable in applications. There were big troubles with it. So one has to keep this in mind when programming systems. When you are adding numbers which are very different, you may introduce an extra error, which is not included in the theory of error propagation. The same thing is happening when you are subtracting numbers. So, for subtraction, you are in trouble when the numbers are too close, you are in trouble when they are too different. So when you are subtracting numbers, ideally you would have numbers which are not quite the same, but not too far, sort of middleish apart. And then you're okay. Multiplication. Here the problem, practical problem, lies in the floating point format. When you write a number in a floating point form, do we have some? Yes, here. The exponent also needs some room in the memory, and this is limited. For instance, in my calculator, I cannot make a larger exponent than 99, which means there is a largest possible number, and if your result exceeds this number, the computer just gives up, or calculator. This is called overflow error. So we have to really worry about overflow errors. Likewise, there is the largest negative number which can be put into the exponent. On my calculator is 10 to negative 99. So when I look at the real line, as my calculator sees it, here is the theoretical real line, here is 0. But on my calculator, there is a smallest positive number which can be entered and stored in memory, and nothing smaller can be put into my computer or calculator. And there is also the largest possible number. This is the range of numbers that my calculator or a computer can store. If some result of calculation goes above, the computer starts complaining and just stops calculating, or calculator. That's the overflow error. If some result falls below the smallest possible expressible number, it automatically becomes 0. This is the underflow error. And you often encounter it with division. Now you may say, okay, if this number is almost 0, then there is no harm in replacing it with 0. The problem is this can be an intermediate step in calculation. So for instance, imagine that you are calculating one of those combinatorial numbers. So you have some big number and factorial on the top and factorial on the bottom. How do you implement it? Well, if you implement it by calculating the factorial and then dividing it by the factorial of the denominator, then this number will be much larger than the eventual outcome. And if you get overflow error here, you will never get to the answer, even though the answer could be reasonably large. On the other hand, if you implement it like that, you first divide by the factorial of the denominator, and then multiply by n factorial, then here you may run into underflow problem. You replace this with 0, and you will never get the correct answer. So one thing that people who program software need to do is to look at calculations and arrange them in such a way that they mitigate the possibility of these two problems. So for instance, when you're calculating something like that, a good idea is to start with 1 or start with n and do something like n divided by k times n minus 1 divided by k minus 1 and things like that. So that you keep multiplying, dividing. And in that way, you are keeping the intermediate results happy, more or less. So there are also tricks how to handle situations when you are adding very tiny numbers with very huge numbers, things like that. I mean, this has been studied because it's very important. So there are some results, there are some procedures that can be followed. And when you are using, as an engineer, some software for critical, real-life critical calculations, you are really hoping that those who programmed it knew their business, knew their job, and did the numerical calculations properly. But you never know. And second, sometimes there are problems which are really, I mean, there is no overall solution that would handle all the problems. It may always happen that there will be a situation that nobody counted on, and then you are in trouble. So it's a good idea to develop intuition, engineering intuition, that you look at a problem and you sort of make a guess, educated guess, how the situation will develop. And then you ask a computer for prediction. And if they are the same, you may say, okay, I was good. You know, I did the same prediction as this computer, which costs, I don't know how many millions. And if those predictions differ, then you can ask, okay, was it me who made a mistake or the computer who made a mistake? And sometimes it's one, sometimes it's the other. But either way, if these predictions do not agree, this shows that you should look at the situation closer, which is always good. Anyway, let's have a look. Okay, let's make room and let's have a look at an example. Okay, what we see here on the top is a nice-looking polynomial, essentially, because we can see powers, like y to power 6, with integer coefficients. All these multiplicative numbers, they are just integers, cute integers, 3 digits, 4 digits. Nothing bad. Just at the end, there is one division. So it's not actually a polynomial, but almost a polynomial, apart from the last expression. And the last expression is not also too bad, because this is just a simple division. Now, this expression was invented by a guy called Rump. I think he was a German. And this surprised a lot of people when they tried playing with it, which we will do as well, because I'm going to evaluate it. I'm going to substitute two numbers for x and y. And these numbers are integers, as you can see, but I will treat them as decimal numbers, forcing computer to work to do the calculations in the floating point format. So let's see what the answer is. The answer is 10 to 29. Is this in some way interesting? Not yet, not yet. So the answer is 10 to 29. Now the trick is, I'm using Maple here, but this isn't really important. The important thing is, the precision of this calculation was 10 digits. Now, my favorite number is 13, so I just wonder whether something would change if I increase precision of calculations to 13, which on the system can be done. So let me ask Pretty please do the calculation again with precision 13 digits, and the answer is 23.45. Now, isn't that quite a big change from 10 to 29? I mean, this is a huge number. Do we have a name for it? Million, billion, trillion, quadrillion, pentamillion, whatever. Google. 10 to 29, this is insanely huge number. And suddenly it's 23 just by changing precision of calculation by 3 digits. Let's ask about 15. So if we ask the system to perform this calculation with precision 15, the answer is negative 10 to 24. Now, this is a big surprise, because we are a huge number here, but on the negative half of the real line. So these two numbers are really far apart, and this one is somewhere in the middle. Okay, this looks like an interesting sport. How about 20 digits precision? With 20 digits precision, the answer is 23.45. So this is becoming the candidate or the favorite if we should guess the answer, but we are not going to guess. We will try higher precision, 25 digits. With precision 25 digits, the result is, okay, I would love to write 10 to 13. I would really love it, but this is almost 10. So it's almost negative 10 to 14. 14 is also a nice number. Okay, let's not be prejudiced against numbers. Okay, 30 digits precision. With 30 digits precision, the outcome is 23.45 and so on. 1, 2, 3, 3 times this number appeared. This is interesting. Let's see what happens with precision 35. Wow, we didn't have this one before either. So if we ask for precision 35 digits, the answer is, let's say, minus 10,000. Quite a list of values to choose from. How about 40 digits precision? With 40 digits precision, the alleged answer is minus 16 point, let's say 55. I rounded this one to 2 digits. Let me do it here as well. This is actually the correct answer. Good question. What precision do you have to use in order to obtain the correct answer? And the answer is, I tried it, of course, but just to show you how this works, with 38 digits, I'm already getting it, but with 37 digits precision, I'm still getting this familiar 23.45. So this shows that the smallest precision, which gives me the precise answer, is 38 digits precision, and nobody uses it in calculations. Real-life calculations are done at much, much lower precisions, which means that operating systems and the softwares for engineers that work in the usual way, they would actually yield totally wrong answers for this calculation. By the way, in electrical engineering field, there is an international association, whatever, and they have guidelines, and the guideline for electrical engineering, real-life electrical engineering, is approximately 15 digits precision, so they would get this answer officially. This is a problem. When this guy Rump came up with this example, a lot of people were unhappy, and they tried to cure their systems of such trouble. Here the problem is that when you do the calculations, you are subtracting numbers which are very similar. And we saw it here. Subtraction of close numbers, that's a problem. And here we can see it nicely. Okay, this is a really, really big problem. So people try to fix their systems, and this Rump guy and some other people just tweaked this example a little bit, and they got the wrong answers again. So yeah, it's really hard to make a calculating system which is totally foolproof. Okay? You can always find some sort of calculation which squeezes through those guidelines and those defenses, and yeah, this is difficult. So this is a really nice example, a very famous Rump example, which shows that the calculations, even with relatively high precisions, can give you totally wrong answers. And they even can suggest things that are sort of, I mean, this is devious, you know, repeating these answers all the time, these wrong answers. So yeah, this is not a happy end to this lecture. So let's try some happy end. Okay, so cases like this are extremely rare. They are artificially prepared, and most real-life engineering calculations, they are much safer, fortunately for us. And anyway, we should be really careful and check the answers. If the computer tells us something, don't trust it, use your common sense, look at it and ask, does it make sense? Does it fit with the picture of the situation I have? Things like that. Anyway, this is essentially the end of the chapter called Error Propagation. We will be drawing on some conclusions later on when we will investigate numerical methods, and we will ask, is it numerically stable? Which means, do the errors on the input totally spoil the answer or not? That's a good question, and this knowledge will come definitely handy. Okay, so we'll refer to it, but the chapter is over. That's also a happy end. Let's have a look at our first numerical method. We mentioned that absolute errors are closely related to errors in measurements. Now, relative errors, they are closely related to working with computers and calculators. Okay, let me start again. We talked about absolute errors being related to measurements. Now, relative errors are closely associated with working in computers and calculators. No. Okay. Last try, for the third time. We talked about relative errors. Okay. We talked about absolute errors being related to measurements. Now, relative errors are closely related to computers and calculators, which also means irrational numbers. No, I'm mixing it up. We talked about absolute errors being related to measurements. Now, relative errors, they are closely related to the way that's in which Jesus, I got totally derailed. Okay, let me try it for the last time, one more time. We talked about absolute errors being closely related to measurement. No, that's... Okay, one more time. We talked about absolute errors being related to measurements. Now, relative errors, they are closely related to the way numbers are stored in computers and calculators. And we will ask, is it numerically stable? Which means, do the errors on the input throw out, or do the inputs on the input, no. Do the errors on the input totally spoil the answer or not?